Welcome to Chapter 13, Aviation Weather Services. In this chapter, we'll take a comprehensive look at the weather tools and resources available to pilots and aviation professionals. Understanding how to access, interpret, and apply weather information is one of the most critical skills in aviation. Weather-related accidents remain a leading cause of fatal incidents in general aviation, which is why proficiency with these services is not just helpful, it's essential. Throughout this chapter, we'll cover the full spectrum of aviation weather resources, from surface observation systems and pilot reports to forecasts, charts, and modern data link technologies. By the end, you'll have a solid foundation for gathering and analyzing weather information to support safe, informed flight decisions. Let's get started. This chapter covers everything a pilot needs to know about obtaining and interpreting aviation weather information. We'll start by looking at the various observation systems used to collect weather data, including surface stations, upper air soundings, radar, and satellites. From there, we'll explore the service outlets available to pilots for getting weather briefings, such as flight service stations and automated telephone services. We'll then move into weather reports, where you'll learn how to decode METARs and pilot reports. After that, we'll cover forecasts and charts, including terminal aerodrome forecasts, area forecasts, AIRMETs, and SIGMETs. Finally, we'll wrap up with a look at modern data link technology, NEXRAD radar, and the responsibilities that come with using electronic weather displays in the cockpit. By the end of this chapter, you'll have a solid foundation for gathering, interpreting, and applying weather information to make sound pre-flight and in-flight decisions. The aviation weather system is not the product of any single agency. It's a coordinated effort involving multiple organizations working together to keep pilots informed and flights safe. The National Weather Service, the FAA, the Department of Defense, private aviation companies, and international weather organizations all contribute to this system. Through rigorous scientific study and sophisticated computer modeling, meteorologists are able to predict weather patterns with ever-increasing accuracy. What this system delivers to you as a pilot is access to up-to-date weather reports and forecasts that support sound decision-making both before and during flight. Whether you're conducting a pre-flight briefing or reassessing conditions en route, these resources are your primary tool for evaluating the weather environment. Understanding why this matters is straightforward. Weather remains one of the leading factors in aviation accidents. The aviation weather system exists to give you the information you need to make confident go, no-go decisions and to actively manage weather-related risks throughout your flight. Knowing who produces this information and how it reaches you helps you better understand its reliability and how to use it effectively. Weather observations fall into 4 distinct categories, and together they form the backbone of every forecast, advisory, and briefing you'll rely on as a pilot. At the surface level, METARs collected from ground stations, as well as automated systems like AWOS and ASOS, give us a continuous snapshot of conditions at airports across the country. Moving up in altitude, upper air data comes from radio sondes carried aloft by weather balloons, along with pilot reports and aircraft-based systems like AMDAR and MDCRS, which gather real-time atmospheric data during actual flights. Radar is your third category, and includes the powerful WSR-88D NEXRAD network, terminal Doppler weather radar, airport surveillance radar, and even airborne radar systems on equipped aircraft. Finally, satellite imagery provides near real-time weather coverage across the entire North American continent, typically accessed through subscription-based services. Understanding where observation data comes from helps you better evaluate its reliability, its limitations, and how current it actually is when you're making a go or no-go decision. Surface aviation weather observations, known as METARs, are one of the most fundamental weather products available to pilots. These reports provide a standardized snapshot of weather conditions at a specific location and time, and knowing how to read them accurately is an essential skill for any aviator. A complete METAR contains several key elements. It identifies the type of report and the station, along with the date and time of the observation. It reports wind direction and speed, prevailing visibility, and runway visual range when applicable. It describes current weather phenomena, sky condition, temperature and dew point, and the altimeter setting. The remarks section can provide additional detail that significantly affects your interpretation of conditions. Many of these observations are generated automatically through two primary systems: AWOS, or Automated Weather Observing Systems, and ASOS, Automated Surface Observing Systems. These systems are part of a broad network of government and privately contracted facilities that provide continuous, around-the-clock weather data. It is important to understand that each individual METAR reflects conditions only within a small radius of that reporting station. However, when you review multiple METARs from stations across a region together, you begin to build a much larger and more accurate picture of the overall weather environment you will be operating in. Upper air observations give meteorologists and aviators a critical picture of what's happening above the surface, and there are several key systems that make this possible. The radio sonde is one of the most fundamental tools in upper air observation. Attached to a hydrogen or helium balloon, this small instrument package ascends at roughly 1,000 feet per minute, reaching altitudes up to 115,000 feet. As it climbs, it transmits temperature, moisture, pressure, and wind data via a low-power radio signal. Over 75,000 radio sondes are launched every year worldwide, though only about 20% are ever recovered. Pilot reports, or PIREPs, are uniquely valuable because pilots are the only real-time source for actual turbulence, icing conditions, and cloud heights aloft. When ceiling drops below 5,000 feet or visibility falls to 5 miles or less, filing a PIREP is required. These reports go to ATC or flight service and are shared with other pilots in the area. Finally, AMDAR and MDCRS represent the modern automated side of upper air data collection. AMDAR generates over 220,000 aircraft observations per day globally, while MDCRS specifically gathers real-time upper air data from more than 1,500 aircraft operating in U.S. airspace through the ACAR's system, forwarding that data directly to the National Weather Service. Together, these systems provide a continuous and comprehensive picture of the atmosphere above us. The primary radar system used in operational meteorology is the WSR-88D, also known as NEXRAD Doppler radar. Understanding how this system works is essential for interpreting weather observations accurately. The WSR-88D operates in two distinct modes depending on current weather conditions. Clear air mode is the most sensitive setting, designed to detect even weak returns in the atmosphere. In this mode, the antenna rotates slowly, and images update approximately every 10 minutes. Precipitation mode increases the antenna's rotation speed, allowing images to refresh every 4 to 6 minutes, giving forecasters more frequent updates during active weather events. Radar returns are measured in decibels of reflectivity, expressed as dBz. This scale tells us the intensity of precipitation. Returns below 30 dBz indicate light precipitation. Values between 30 and 40 dBz suggest moderate intensity. The 40 to 50 dBz range corresponds to heavy precipitation, while anything above 50 dBz is considered extreme and often associated with severe thunderstorms, large hail, or intense rainfall. As you analyze radar imagery, paying close attention to these reflectivity values will help you quickly assess the severity and potential impacts of ongoing precipitation systems. Radar systems display precipitation intensity using decibel Z or dBz scales, and it's important to understand that these scales differ depending on the operational mode. In clean air mode, the scale is more sensitive, detecting lighter returns like dust, insects, and light precipitation. In precipitation mode, the scale shifts to capture the broader range of intensities found in heavier weather events. Always be aware of which mode is active when interpreting radar imagery. Beyond the standard WSR-88D network, several specialized radar systems play critical roles in aviation safety. The Terminal Doppler Weather Radar, or TDWR, is installed at major airports specifically to detect wind shear, gust fronts, and heavy precipitation in the immediate vicinity of runways, providing real-time alerts to air traffic control. Airport surveillance radar is primarily designed to track aircraft, but it also detects precipitation location and intensity, helping controllers route traffic safely around developing weather. Finally, airborne radar is carried on board the aircraft itself, operating in either the C or X band at approximately 6 or 10 gigahertz respectively. These frequencies allow the system to penetrate heavy precipitation and identify thunderstorm cells, giving flight crews a direct, real-time picture of weather along their route of flight. When planning a flight, knowing where to get accurate and timely weather information is just as important as understanding the weather itself. There are several aviation weather service outlets available to pilots, each serving a specific purpose. The Flight Service Station, or FSS, is your primary pre-flight weather source. It's available around the clock by calling 1-800-WX-BRIEF. FSS specialists can provide standard, abbreviated, or Outlook briefings, as well as in-flight updates and weather advisories while you're en route. The Telephone Information Briefing Service, or TIBS, offers automated recordings covering meteorological and aeronautical information for specific areas and routes. It's a useful preliminary tool, but keep in mind, it requires touch-tone access and is not a substitute for a full FSS briefing. AWOS, the Hazardous In-Flight Weather Advisory Service, continuously broadcasts hazardous weather information over selected VOR facilities across the contiguous 48 states. This includes AIRMETs, SIGMETs, convective SIGMETs, and urgent PIREPs. You can identify AWOS-equipped VORs on your sectional chart by looking for the letter H in the navigation box. Finally, for pilots operating in Alaska, the TWEB, Transcribed Weather Broadcast, provides continuous automated weather over low and medium frequency and VHF VOR facilities, covering adverse conditions, surface observations, PIREPs, and density altitude information. When reviewing a sectional chart, you can quickly identify which VORs offer AWOS capability by looking for the letter H in the upper right corner of the VOR identification box. This simple symbol tells you that hazardous in-flight weather advisories are being continuously broadcast on that station's frequency. Keep in mind that AWOS provides a summary broadcast, so if you need more detailed or specific weather information, you should contact a flight service station or en route flight advisory service for assistance. Shifting to ARTCC radar weather, air route surveillance radars track transponder returns and can display weather information to controllers. On newer display systems, weather is shown in 3 shades of blue, representing varying levels of precipitation intensity. Controllers have the ability to select how much weather data appears on their screens. But here is an important point for pilots. You should never assume that a controller is continuously monitoring weather returns. Because weather data overlaps and can obscure aircraft data blocks, controllers will often reduce or remove the weather display to maintain separation. Do not rely on ATC as your primary source of weather avoidance information. Before every flight, you should obtain a weather briefing from a flight service station specialist. When you call, be prepared to provide essential information. Whether you're flying VFR or IFR, your aircraft identification and type, departure point, estimated time of departure, planned altitude, route of flight, destination, and estimated time en route. This helps the specialist tailor the briefing to your specific flight. There are 3 types of briefings you need to know. The standard briefing is the most comprehensive and should be used before any flight. It covers adverse conditions, a VFR not recommended advisory if applicable, a weather synopsis, current conditions, en route and destination forecasts, winds aloft, NOTAMs, and any ATC delays. The abbreviated briefing is a shortened update. Use it when you've already received a prior briefing and need to update it, or when a departure has been delayed. Always tell the specialist when and where you got your last briefing so nothing important gets left out. Finally, the Outlook briefing is used when your departure is 6 or more hours away. It gives you an initial look at forecast trends to help with early planning. However, always follow up with a full standard briefing closer to your actual departure time to ensure you have the most current and complete weather picture. Let's break down how to read a METAR, which is the standard format used for aviation routine weather reports. The example on this slide represents a fairly significant weather situation, so it's a great one to decode. Starting from the left, METAR tells us this is a routine weather observation, and KGGG identifies the station as Gregg County Airport in Texas. The date-time group, 1161753Z, means this report was issued on the 16th day of the month at 1753 Zulu, or UTC. The modifier auto tells us this came from an automated station with no human observer on site. Moving to wind, 14-1G26KT means the wind is out of 140 degrees at 21 knots, gusting to 26 knots. Visibility is reported at 3/4 of a statute mile, which is quite low. The weather group, plus TSRA-BR, tells us there's heavy thunderstorm activity with rain and mist. That plus sign indicating heavy intensity is important to recognize quickly. Sky condition shows a broken ceiling at 800 feet and an overcast layer at 1,200 feet, with cumulonimbus clouds present. Temperature and dew point are nearly identical at 18 and 17 degrees Celsius, indicating very high humidity. The altimeter setting is 29.70 inches of mercury. Finally, the remarks section contains PRESFR, meaning pressure is falling rapidly, a strong indicator of deteriorating conditions. This is a report that demands immediate pilot attention. When reading a METAR, two of the most important elements to decode are sky cover and present weather. Let's walk through both. Sky cover is reported using standard contractions based on how much of the sky is covered in eighths, or octas. SKC and CLR both indicate a clear sky with less than 1/8 coverage. Few covers that same range but extends up to 2/8. Scattered, coded as SCT, means 3 to 4/8 of the sky is covered. Broken, or BKN, indicates 5 to 7/8 coverage and is considered a ceiling. Overcast, OVC, means the sky is completely covered at 8/8. For present weather, intensity is indicated by a symbol placed before the weather code. A minus sign means light, no symbol means moderate, and a plus sign means heavy. VC indicates the weather is in the vicinity, roughly 5 to 10 miles from the airport but not at it. Weather codes are often combined using descriptors and precipitation types. For example, TSRA means thunderstorm with rain, and FZFG means freezing fog. Common descriptors include TS for thunderstorm, SH for showers, and FZ for freezing conditions. Precipitation types include RA for rain, SN for snow, GR for hail, and PL for ice pellets. Understanding how these elements combine is essential for accurately interpreting any METAR report. Pilot weather reports, or PIREPs, are one of the most valuable tools available to a pilot because they capture real-time conditions that no forecast or ground-based observation can provide. When another pilot reports actual cloud bases and tops, wind shear, turbulence, or icing along a specific route, that information is immediately actionable. It's worth noting that ATC is required to solicit PIREPs whenever the ceiling drops below 5,000 feet, or visibility is at or below 5 miles, which tells you how critical this data becomes in marginal conditions. Let's look at the example on screen. This is a routine PIREP filed 25 nautical miles on the 090-degree radial from the Gregg County VOR at 1450 Zulu from a Cessna 182 at 6,000 feet. The pilot reported an overcast layer at 8,000 feet, 4 miles visibility in rain, a temperature of 5 degrees Celsius, winds from 270 at 30 knots, light turbulence, and heavy rain. When you file your own PIREP, the first 5 elements, type, location, time, altitude, and aircraft type, are mandatory, along with at least one observed weather phenomenon. Getting comfortable with this format means you contribute to a system that benefits every pilot flying behind you. A terminal aerodrome forecast, or TAF, is one of the most important weather products you will use in flight planning. It provides a detailed weather forecast for a specific airport, covering a 5 statute mile radius around that airport. TFs are valid for either 24 or 30 hours and are issued 4 times daily at 00,000, 0600, 1200, and 1800 Zulu. Importantly, TFs use the same descriptors and formatting conventions as METARs, so once you know how to read one, the other becomes much easier. Every TAF includes key elements: the type, either routine or amended, the ICAO station identifier, the date and time of issuance, the valid period, and the forecast conditions including wind, visibility, weather, and sky condition. Pay close attention to change groups. FM indicates a rapid, permanent change in conditions from that point forward. Tempo indicates temporary fluctuations lasting less than 1 hour. PRLB 30 indicates a 30% probability of thunderstorms or significant precipitation, though this group will never appear in the first 6 hours of the forecast. Looking at our example, KPIR was issued on the 11th at 11:30 Zulu and is valid from 1200 Z on the 11th through 1200 Z on the 12th. From 1500 Z, expect winds from 160 degrees at 15 knots gusting to 25. The PRLB 30 group tells us there is a 30% chance of thunderstorms with reduced visibility and cumulonimbus clouds between 1200 Z and 1400 Z. The Aviation Area Forecast, commonly referred to as the FA, provides pilots with a broad picture of clouds, general weather conditions, and visual meteorological conditions expected across a large multi-state region. It is issued 3 times daily, remains valid for 18 hours, and 6 forecast areas together cover the entire contiguous 48 states, centered on Salt Lake City, Chicago, Boston, San Francisco, Dallas, Fort Worth, and Miami. The FA is organized into 4 distinct sections. The header identifies the source, issuance date and time, valid period, and the geographic area covered. Next, the precautionary statements section alerts pilots to IFR conditions, mountain obscurations, and thunderstorm hazards. An important reminder here is that all heights in the FA are given in MSL unless specifically noted as AGL or ceiling. The synopsis section follows, offering a brief summary of pressure systems, fronts, and general circulation patterns affecting the region. Finally, the VFR clouds and weather section provides the detailed forecast you will use most directly: expected sky conditions, visibility, and significant weather for the next 12 hours, along with a 6-hour outlook beyond that. When planning a cross-country flight, always identify which FA region or regions you will be flying through and review each section carefully before departure. In-flight weather advisories are critical tools for understanding hazardous conditions along your route, and they come in 3 distinct types, each serving a specific purpose. AIRMETs, designated with the WA identifier, are issued every 6 hours and focus on conditions that are particularly hazardous to light aircraft. There are 3 types to remember. Sierra covers IFR conditions and mountain obscuration. Tango addresses turbulence and sustained surface winds of 30 knots or greater, and Zulu deals with icing and freezing levels. SIGMETs, using the WS identifier, step up in severity and apply to all aircraft, not just light ones. They cover non-convective hazards such as severe icing, severe or extreme turbulence, clear air turbulence, dust or sandstorms reducing visibility below 3 miles, and volcanic ash. SIGMETs are valid for 4 hours or 6 hours when associated with a hurricane, and are issued alphabetically from November through Yankee. Convective SIGMETs represent the most urgent thunderstorm-related hazards. They are issued when severe thunderstorms produce surface winds exceeding 50 knots, hail 3/4 of an inch or larger, or tornadoes. They also cover embedded or line thunderstorms and heavy precipitation, affecting 40% or more of a 3,000 square mile area. These are valid for 2 hours and are issued at 55 minutes past each hour. Always check for these before and during flight. The winds and temperatures. A loft forecast, or FB, gives pilots detailed information about upper-level wind and temperature conditions along a planned route. These forecasts are issued twice daily, based on radio sonde balloon data collected at 0000 and 1200 Zulu. A few important boundaries to remember. Altitudes through 12,000 feet are expressed as true altitudes, while 18,000 feet and above are given as flight levels. Wind direction is always referenced to true north, speed is in knots, and temperature is in degrees Celsius. No wind forecast is provided within 1,500 feet of the station elevation, and no temperature is given within 2,500 feet of that elevation. The code 9900 means winds are light and variable, calm or less than 5 knots. Decoding high-speed winds requires a specific technique. When the encoded direction digits exceed 50, you subtract 50 from the direction and add 100 to the speed. So the code 731962 decodes to 230 degrees at 119 knots with a temperature of negative 60 degrees Celsius. When speed reaches 200 knots or greater, it is always coded as 99 knots, meaning 7799 represents 270 degrees at 199 knots or more. Notice in the table that the DAN station shows a dash at 6,000 feet. That means no forecast was issued because that altitude falls within 1,500 feet of the station elevation. The surface analysis chart is one of your most essential weather planning tools. Transmitted every 3 hours, it gives you a current snapshot of surface weather conditions across the contiguous 48 states. Each location on the chart uses what's called a station model, a standardized arrangement of symbols and numbers that packs a tremendous amount of information into a small space. At a glance, you can read sky cover, temperature, and dew point for any reporting station. Pressure information is also encoded at each station. You'll find the sea level pressure reported to the nearest tenth of a millibar, along with the pressure change and tendency over the past 3 hours, which tells you whether conditions are improving or deteriorating. Present weather is depicted using a set of more than 100 standard symbols, covering everything from light drizzle to severe thunderstorms. Wind is shown using barbs extending from the station circle. A short barb represents 5 knots, a full barb equals 10 knots, and a pennant-shaped flag indicates 50 knots. By counting the barbs and pennants, you can quickly determine wind speed and direction. Understanding how to read a station model efficiently takes practice, but mastering it gives you a powerful ability to assess surface conditions anywhere along your route. The weather depiction chart is a valuable pre-flight planning tool prepared every 3 hours using data collected from METARs across the country. It gives you a quick visual snapshot of flight conditions by dividing airspace into 3 categories. IFR conditions are shown as hatched areas with a smooth outline, indicating ceilings below 1,000 feet and visibility less than 3 miles. Marginal VFR, or MVFR, appears as a smooth outlined area without hatching, covering ceilings between 1,000 and 3,000 feet with visibility between 3 and 5 miles. VFR conditions have no outline at all, meaning ceilings are above 3,000 feet and visibility exceeds 5 miles. The Significant Weather Prognostic Chart, or PROG chart, takes things a step further by forecasting what conditions are expected to look like. Issued 4 times daily at the standard UTC times, it covers airspace from the surface up to flight level 240. This 2-panel chart displays freezing levels, areas of IFR and MVFR, moderate or greater turbulence, frontal systems, pressure patterns, and precipitation type and intensity. For longer range planning, 36 and 48-hour prognostic charts are issued twice daily, allowing you to anticipate weather trends well in advance. Together, these charts give you a comprehensive picture of both current and forecast conditions before you ever leave the ground. The 36 and 48-hour surface prognostic charts extend the forecast picture beyond the shorter-range 12 and 24-hour progs, giving pilots and weather briefers a look further into the future. Like their shorter-range counterparts, these charts depict the forecast positions of high and low pressure systems, frontal boundaries, and areas of expected precipitation. They are issued twice daily, providing continuity with the nearer-term forecasts. Because these charts project conditions further out in time, the inherent uncertainty in the forecast increases, so they should be interpreted with that in mind. They are most useful for flight planning purposes when you need a general sense of how a weather system is expected to develop or move over the next day or two. For example, if a significant low-pressure system is forecast to deepen and track across your intended route within 48 hours, this chart gives you early awareness to consider alternate plans. Always use these extended prognostic charts in combination with the shorter-range products and current observations to build the most complete and accurate picture of expected conditions. When receiving weather information from air traffic control, it's important to understand the limitations of what they can and cannot tell you. ATC radar systems identify all weather returns simply as precipitation. They have no ability to distinguish between rain, snow, hail, or virga. Keep that in mind when interpreting any weather picture they provide. Most air route traffic control centers use the Weather and Radar Processor, or WARP, which displays NEXRAD mosaic data. When WARP is available, precipitation intensity is described as light, moderate, heavy, or extreme. However, that data can be up to 6 minutes old, meaning conditions may have changed significantly from what the controller is describing. When WARP is unavailable, controllers fall back on narrowband air route surveillance radar, which only provides 2 intensity levels, moderate and heavy to extreme. And in some cases, the controller may have no intensity data at all, in which case they'll advise you that intensity is unknown and simply describe the location of the precipitation relative to your position or a geographic reference. One critical point: ATC radar cannot detect turbulence under any circumstances. Just because a controller clears you through an area doesn't mean it's free of hazards. Always expect turbulence near convective activity and exercise extreme caution when operating within 20 miles of any thunderstorm. The decision to deviate remains yours as pilot in command. When you need help avoiding hazardous weather in flight, ATC can be a valuable resource. Controllers are able to issue pertinent weather information and assist pilots in navigating around dangerous areas, but you need to know how to ask for what you need. There are 4 main types of assistance you can request. First, you can request a course deviation. Simply state the number of miles and the direction you need to deviate from your current course. Second, you can request an entirely new route that avoids the affected weather area altogether. Third, if the weather is at your current altitude, you can request an altitude change to find clearer conditions. Finally, you can request radar vectors, where the controller actively guides you around the affected areas using their radar picture. Here is the critical point to understand. Weather avoidance assistance is a secondary function for ATC. The controller's primary responsibility is aircraft separation, and that will always take priority. Weather assistance will only be provided when it does not interfere with that primary duty. This means there may be times when a controller cannot accommodate your request immediately, or at all. As the pilot in command, you must never rely solely on ATC for weather avoidance. That responsibility ultimately belongs to you. Many modern aircraft are equipped with electronic flight display systems that integrate data link weather services directly into the cockpit environment. This capability gives pilots access to a comprehensive suite of weather products without having to rely solely on pre-flight briefings or ATC weather updates en route. The range of available weather products is extensive. Pilots can access graphical NEXRAD radar data overlaid directly on navigation displays, along with both graphical and textual METAR and TIAF information. Additional products include graphical wind data, echo tops, and cloud tops, which are especially valuable for altitude planning. The system can also display lightning strike data and storm cell movement, helping pilots anticipate developing hazard areas. Beyond convective weather, pilots can access SIGMETs and AIRMETs, surface analysis charts, county-level severe weather warnings, freezing level data, hurricane tracks, and temporary flight restrictions. The Garmin G1000 shown here is a common example of an integrated glass cockpit system offering this full range of products through its weather menu. Understanding what products are available and how to interpret them in flight is a critical skill. Having this data in the cockpit enhances situational awareness significantly, but remember, data link weather is not real-time. There is always a delay, so it should be used to support your decision-making, not replace a thorough pre-flight weather briefing. NEXRAD is one of the most powerful weather tools available to pilots, but it also comes with some of the most serious and frequently misunderstood limitations in aviation weather. The system comprises 159 WSR-88D radar sites across the United States and select overseas locations, and it's a joint venture among the Departments of Commerce, Defense, and Transportation, managed cooperatively by the NWS, the Air Force Weather Agency, and the FAA. The coverage is impressive. Data range extends up to 2,000 miles. But here's where pilots must pay close attention. The radar image you see in the cockpit can already be up to 5 minutes old by the time it reaches your display. In cases of high data latency, the actual age of that image can exceed what your cockpit display indicates by 15 to 20 minutes or more. The NTSB has investigated fatal accidents where pilots made penetration decisions based on NEXRAD imagery that no longer reflected reality. This is the foundational principle you must internalize. NEXRAD shows you where weather was, not where it is. Convective weather moves, grows, and intensifies rapidly. Never use NEXRAD as a substitute for onboard storm avoidance radar, and never use it to navigate through or between cells in a line of storms. It is a strategic planning tool, not a tactical penetration tool. NEXRAD. A powerful weather tool in the cockpit, but understanding its limitations is just as important as knowing how to use it. When you zoom out to the 500-mile range, you'll notice that the individual color gradient blocks become clearly visible, which gives you a good picture of large-scale weather patterns but sacrifices fine detail. Let's talk about the key limitations. First, base reflectivity only shows you precipitation intensity. It cannot tell you whether you're looking at rain or hail, and it cannot depict cloud layers or identify storms that are directly overhead the radar station. That blind spot directly above the station is an important operational consideration. Resolution is another factor. NEXRAD has a minimum resolution of 1.24 miles, meaning at close range, you'll start to see individual square return boxes on the display. This pixelation can make precise storm boundary identification more difficult. You also need to be aware of display abnormalities. Ground clutter, sunstrokes, shadows cast by buildings or mountains, military chaff, and spurious data can all introduce false returns or obscure real weather on the screen. Finally, and this is critical from a display management standpoint, NEXRAD is mutually exclusive with topo, terrain, and storm scope overlays. Activating NEXRAD will automatically disable those layers, so always be deliberate about which information you need most for the phase of flight you're in. When using in-cockpit NEXRAD, there are 4 critical practices every pilot needs to follow. First, truly understand latency. Many pilots assume the data is only 5 minutes old based on the age indicator, but the actual conditions you're looking at could be 15 to 20 minutes behind reality. In fast-moving weather, that gap can be the difference between a safe decision and a dangerous one. Second, always complete a thorough pre-flight weather briefing before you leave the ground. In cockpit. NEXRAD is a powerful tool, but it is not a substitute for a full briefing from a qualified source. Third, never rely on NEXRAD alone in flight. Use all available weather information sources together to build the most accurate picture of conditions along your route. And fourth, share what you know. Many pilots are unaware of these limitations, so educating fellow aviators about NEXRAD's constraints is a genuine contribution to the safety culture we all depend on. Used wisely and with full awareness of its limitations, in-cockpit NEXRAD is a valuable asset. Used without that understanding, it can create a false sense of security at exactly the wrong moment. Modern multi-function displays give pilots a powerful advantage by presenting complex weather advisory information in a clear, visual format directly on the moving map. When AIRMETs and SIGMETs are overlaid on the MFD, they appear as dashed boundary lines covering display ranges of up to 2,000 miles. A color-coded legend box identifies each hazard category at a glance, including icing, turbulence, IFR conditions, mountain obscuration, and surface winds. This eliminates the need to manually plot advisory boundaries from a textual description, allowing pilots to immediately see where hazards exist relative to their route. Graphical METARs take this one step further by providing real-time surface weather conditions at individual reporting stations. Each airport symbol displays a color-coded flag that instantly communicates the current flight category: green for VFR, blue for marginal VFR, red for IFR, and magenta for low IFR. Because pilots can pan across a 2,000-mile range, They can quickly scan conditions along the entire planned route and identify areas where flight conditions may be deteriorating. Together, these two display features allow for more efficient pre-flight planning and better in-flight situational awareness regarding weather hazards. Data link weather has fundamentally changed how pilots access weather information in flight. In the past, pilots were limited by radio range and had to rely on flight service station personnel, who could only communicate with one pilot at a time. Data link removes both of those barriers entirely. With data link technology, pilots can now receive continuously updated weather across the entire country, regardless of altitude or geographic location. This gives you a much more complete and current picture of the weather environment surrounding your flight. There are two primary categories of data link devices. The first is FAA-certified installed avionics. These are panel-mounted systems that meet FAA certification standards specifically for weather data display in the cockpit. The second category includes portable data link receivers, which transmit weather information to tablets and portable display devices. These portable solutions have become increasingly popular due to their accessibility and relatively low cost. Understanding which type of system you're using matters, because certification standards and data reliability considerations can differ between installed and portable solutions. Regardless of the device, Data link weather is a powerful situational awareness tool, but as we'll discuss, it must be interpreted and used correctly to support safe decision-making. Flight Information Service Broadcast, or FISB, is a ground-based broadcast service that transmits aviation weather and aeronautical information directly to your cockpit through the ADS-B network on the 978 MHz UAT data link. If your aircraft is equipped with a compatible receiver, you have access to a wide range of weather and airspace products right on your flight deck display. Those products include METARs and species, TAFs and amendments, NEXRAD precipitation maps at both regional and CONUS scale, NOTAMs, AIRMETs, SIGMETs, convective SIGMETs, special use airspace status, TFRs, winds and temperatures aloft, PIREPs, and TIS-B status. That is a comprehensive set of situational awareness tools available in the cockpit. However, there is a critical limitation you must understand. FISB products are for information and situational awareness only. They do not meet the safety and regulatory requirements of official weather sources, and they should never be used as your primary weather reference. Perhaps most importantly, the data you are looking at can be anywhere from 20 to 30 minutes old. In a dynamic weather environment, that delay is significant. Always consult your specific equipment manual to understand the exact latency for each product, and always cross-reference with official sources before making weather-related decisions. The safety benefits of data link weather are only realized when the pilot truly understands what the system can and cannot do. This responsibility cannot be delegated to the technology itself. Start with product latency. NEXRAD imagery displayed in the cockpit is always a minimum of 7 to 8 minutes older than the timestamp shown on screen. That means the actual weather you are looking at could be significantly different from what the radar captured. Use this data for broad strategic avoidance only, never for maneuvering in close proximity to convective activity. Know your update cycles. Each weather product refreshes on a different schedule, and your data link service provider adds additional delay on top of that. Understand both. Be aware of coverage limitations. Ground-based radar systems may have little to no coverage below 5,000 feet AGL, and NWS NEXRAD has known gaps, particularly across the western United States. Monitor for system failures, both partial and total, and know how your avionics or EFB indicates those conditions. Finally, manage your information load carefully. Layering too many data products simultaneously can degrade your situational awareness rather than improve it. Display only what is relevant to your current phase of flight. Remember, you remain fully responsible for the proper use and correct interpretation of all data link products. The FAA practical test standards may evaluate exactly that. This composite image brings together the key elements of aviation weather services that we have covered throughout this course. You can see how surface weather maps and radar weather maps work alongside color-coded precipitation intensity displays to give pilots a comprehensive picture of atmospheric conditions. Each of these tools serves a distinct purpose, yet they are most powerful when used in combination. The cockpit instrument panel shown here represents the critical point where all of that information converges, where a pilot must synthesize data from multiple sources and translate it into real-time flight decisions. Understanding each individual service is important, but the true skill lies in integrating them effectively. As you continue your training, practice reading these resources together rather than in isolation. Weather decision-making in aviation is rarely based on a single source, and building the habit of cross-referencing multiple services will make you a safer and more confident pilot. Let's take a moment to review the key reference information covered in this section. When interpreting WSR-88D radar returns, intensity is measured in decibels of reflectivity, or dBz. Returns below 30 dBz indicate light precipitation. 30 to 40 dBz indicates moderate, 40 to 50 dBz indicates heavy, and anything above 50 dBz is considered extreme. These same terms, light, moderate, heavy, and extreme, are used directly in ATC radar weather advisories, so the terminology translates straight from the radar reading to the phraseology you'll use on frequency. Regarding operational status codes, PPIN means the radar is operating normally and echoes have been detected. PPIN-A indicates the observation is not available, and PPIM means the radar is inoperative or out of service. The auto code identifies an automated report from a WSR-88D system. Finally, when radar intensity is depicted using symbols, the absence of a symbol indicates light precipitation. A single plus sign is moderate, double plus is heavy, triple plus is very heavy. The letter X indicates intense, and double X represents extreme. Knowing these codes and symbols ensures you can quickly and accurately interpret radar weather information in an operational environment. As we close out Chapter 13, let's reinforce the most important principles you've covered. Weather observation is the foundation of everything. Surface METARs, upper air soundings, PIREPs, radar, and satellite data all work together to give forecasters and pilots an accurate picture of current conditions. Before every flight, get a proper pre-flight briefing by calling 1-800-WX-BRIEF. Whether it's a standard, abbreviated, or Outlook briefing, that phone call is non-negotiable, and nothing in the cockpit replaces it. Learn to read and interpret your reports. METARs, TAFs, PIREPs, AIRMETs, SIGMETs, and winds aloft forecasts. Each tell part of the story. No single source gives you the complete picture, so always cross-reference multiple products. And when it comes to data link weather, remember that NEXRAD and FISB imagery can be 15 to 20 minutes old. Use it for broad strategic decision-making and avoidance, never for navigating through or near active storms. The bottom line is this: no forecast is perfect, but pilots who consistently use all available tools, reports, charts, forecasts, and in-cockpit data, are the ones who make the safest, most informed decisions every time they fly. Weather is not static, and neither is a pilot's responsibility to understand it. Every flight begins with a commitment to gathering the best information available and interpreting it intelligently. Throughout this chapter, we've explored the full ecosystem of aviation weather services, from surface observations and PIREPs to TAFs, METARs, AIRMETs, SIGMETs, and the growing suite of data link tools available in the cockpit. The takeaway is this: no single product tells the complete story. Skilled pilots observe by collecting all available weather data before departure and remain vigilant for updates during flight. They analyze by cross-referencing multiple sources, recognizing that each product has its own limitations and areas of uncertainty. And they decide by applying sound aeronautical decision-making, weighing the risks, considering the alternatives, and never allowing schedule pressure or optimism to override what the data is telling them. Weather will always carry an element of uncertainty. Your job as a pilot is to reduce that uncertainty as much as possible, know when the picture is clear enough to proceed safely, and know when it is not. Fly informed and fly safe.